Right, now we change the topic. We will still talk about the applications of Schwarzschild lemma, but now it's a problem on maybe it's also on geometry, but over the finite field. Right. So let me start with the original Kakeya's problem. So Soichi Kakeya is a Japanese mathematician and who made the following problem. Right. So in 1917, he asked the following: what is the smallest area of some body on the plane such that one can rotate a needle of length 360 degrees, right? So I have a needle. Maybe I have a really small room. So if I want to rotate, if the room is too small, probably, I mean, like this one, there's no way to rotate all the way because it will be stuck, right? So what is the smallest area that you can make so that you can rotate this needle 360 degrees? And such a set is a Kakeya set. Right? So there's a Kakeya set if there's a way of rotating a needle 360 degrees. Right? Or in other words, okay, let me say more generally. So in Rn, a set X is a Kakeya set if it contains line segments of length 1 in every direction. Right? So whenever I pick a vector of some directions, I have some line segments parallel to that, and which is completely contained in my set. Then it's called the Kakeya set. Now, what's funny is that you may imagine that the Kakeya set would have some lower bound on the area, right? But actually, that's not true. Right? So, in fact, surprisingly, for every epsilon, there is a Kakeya set of of area less than epsilon. What? So there's no lower bound. You can make a really tiny Kakeya set where you can rotate your needle 360 degrees. There's a Wikipedia article, so you may look at it. Maybe I can show it to you. Right? Normally you'd imagine that maybe this kind of shape would be the best possible, but actually Piskovich was able to show that for any epsilon there's a Kakeya set whose area is smaller than epsilon, and yet you can rotate the needle 360 degrees. There. That's That's the, and then there are pictures like this. All right. So over the, yeah, so if we have a real field, then this is the situation. Now, there's a conjecture about Kakeya's set in Rn, and whether they have a Hausdorff dimension and least n or not. And this conjecture is still open for all n and is 3. But anyway, my attention is not about this, the original Kakeya set. I'll talk about the Kakeya set in the finite field. So this was proposed. So Kakeya set over a finite field proposed by Wolf in 1999. So for a finite field F, a Kakeya set in Fn is a subset E of Fn containing at least one affine line parallel to every direction in Fn minus 0. So that means what? In other words, E is a Kakeya set if and only if for all vector v in Fn minus 0 there is C in Fn such that C plus V, okay, TV, where T is in the finite field, is completely contained in E. Right? So any directions, you have some. So whenever you have a vector, you can find the parallel line which is completely contained in E. And then he made the following conjecture. The conjecture is, unlike the usual geometric problem where you don't have a lower bound on the size of Kakeya set, in the finite field, so this was proposed by Wolf. Okay, if K is a Kakeya set in f of n, then size of K is big, some constant times f to the n. Right, that was the conjecture, and initially he proved some partial result. So the partial result was that K is at least Cn times f to the n plus 2 over 2 with some sophisticated method. So at that time, this problem was, experts in the field thought that this problem is extremely difficult because even with this proof by Wolf was extremely difficult. But then in 2008, Jeeves de Vere showed one-page proof proving the conjecture. So that's what I'm going to show you. So here's a theorem by de Vere in 2009. right? So if K is a Kakeya set in f of n, then K is bigger than f plus n minus 1, choose n, which is actually bigger than f to the n over m factorial. All right, now let's see how you can prove this. So here's a lemma. So we're gonna use some polynomials, right? So f we have polynomial with n variables and has degree of degree at most q minus 1 over this field. And let's say, what is q? F is q. And let K be a Kakeya set in f to the n. If this polynomial is 0 for all values in K, then f itself is a 0 polynomial. That's the lemma. So if I have a polynomial of degree at most q minus 1, such that at any x inside Kakeya set is 0, then it is identically 0. All coefficients are 0. That's the lemma. So suppose not. So suppose f is not a 0 polynomial. So let us write f of x 1 xn as a sum of fi of x1 up to xn from 0 to let's say d, where d is the degree of f and fi is the homogeneous polynomial of degree I. So that means I'm collecting all the monomials of degree I, and that's gonna be fi. But sometimes you don't have any monomial of degree I. In that case, fi is 0. Right? So I have some of these homogeneous polynomials. And since f is not identical, it's not a f is non-zero polynomial, and f of x is not f of x is 0 for all x in K. Does that mean D is positive? Why? If D is constant, no, if D is 0, if it's constant polynomial, then in order to make a Kakeya set, I mean, you must have, right? So, I mean, trivially, yeah, I mean, there's no way to make f of x to be 0 for all x in K, right? If you have a degree 0 polynomial, because degree 0 polynomial is constant function. But if you have a constant function which makes 0, then it has to be identically 0. So it's 0 polynomial. But we already assumed that f is not a 0 polynomial. So D's degree is bigger. So that means f of D is not a 0 polynomial. Right? F of D is non-zero. So let's choose a vector in f of n minus 0, so non-zero vector. Then there is w, which is some base points such that w plus tv is completely contained in K because it's Kakeya set. Now let's look at this polynomial. So that means f of w plus tv is 0 for all t. Alright? Now let's let GWV, so this is a polynomial indexed by WMV, and then this, let's this to be f of w plus tv. And this is a polynomial with a single variable t. And the degree of GWV is, of course, it's less than or equal to d, which is less than q, right? So the degree of this polynomial is less than q. And every t is the root of g, right? Right, so GWT is 0 for all t. What does that mean? So you have a polynomial whose degree is less than the size of finite field, and it is 0 for every field element. What is that? That means GWV is identical to 0. Right? So all the coefficients are 0. Okay? And so that means coefficients of t to the d is 0. So what is coefficient of t to the d? When do you have t to the d? Well, that's when you have degree d homogeneous polynomial, right? So we are evaluating f with, so these are replaced by wi plus tvi, right? And then we have these polynomials, you're making product of these things. And the coefficients of t to the d, what is that? Well, that is if I want coefficient of t to the d, then I can put w to be 0 and t to be 1 and put v. And I'm interested in d, right? So that is the coefficients. Right? I think of the situation, right? wi, if I make a wi to be 0, then whenever I multiply any wi, then whole term becomes 0. So the coefficients of t to the d is when you never multiply any wi, so the only thing that's left is the vi's and t to the t, right? Because it's the highest order term, so you never get t to the d unless you have f of d. And inside f of d, I cannot multiply any wi, so I can put w to be 0. So this value is precisely the degree of, coefficients of t to the d in GWV. So we know that f of d v is 0 for all v in f of n minus 0. And what happens if and actually this is true even if v is 0, right? Because it's degree d polynomial, degree d homogeneous polynomial. So even if v is 0, this is true. Now d is less than q. So by Schwarzschild, number of roots. So fd is completely 0, or the number of roots of f is at most degree number of roots divided by all possible cases. Okay, that means number of roots is degree to the, okay, degree is what? D, and number of assignment is q, and q to the n, right? So d times q to the n minus 1. But we knew that the number of roots is 0 for all v, so that means number of roots is actually q to the n, right? Any v is a solution, and number of possible v is q to the n, and q to the n is strictly bigger than this, so that means f is identically 0, fd is identically 0, contradiction, right? So that proves the first lemma. So if you have a Kakeya set, and if you have any polynomial which is 0 on the Kakeya set, and it's completely 0. Now, here's a second good lemma. If, okay, let's say if E is a subset of f to the n, the E size of E is less than n plus d, choose D, then there exists a polynomial f of degree at most d, okay, I should say non-zero polynomial, such that f of x is 0 for all x in E. So this says that it's possible to construct a polynomial which is non-zero, and but on my favorite subset it is 0, as long as this subset is small. How do we construct such a thing? So what I do is think of the vector space VD of polynomials with the n variables. Yeah, this is, so n is the number of variables, right? Also dimension too, right? So with n variables of degree and most d has dimension what? What is the dimension of that? Remember? Like it's the number of ways to choose things like a1. So let's say I need to take x1 a1, x2, a2, xn, an, right? So how many ways can I take this monomial? Like I need to select these AIs whose sum is at most d, and each AI is at least 0. So what is the number of ways to choose integers a1 up to an so that these two inequalities are true? And the way you do is like you have this d minus 1, no, n minus 1 plus signs, right? So what I do is I have a d1s and n minus 1 pluses. So then I take a permutation of these symbols, 1 and pluses. And any permutation gives me a monomial, right? Or choice of AIs. And such a thing. Oh, but it's at most d. So how do I fix it? Well, let's add one more parameter. Let's say b, right? So then I have a n pluses and d1s, right? So b is also now I can say it's 0, right? So the number of solutions of this equation is going to be the number of ways to select the monomials of degree at most d, and that is n plus d choose n, or d, right? Same thing. All right. Now let t be the linear function, linear transformation such that t of f is f of a. Right, so any polynomial I give some value, and I mean I give a value, but the value is a vector, right? So f of a indexed by elements in E, and E is my set, right? Now remember, size of E is n plus d less than n plus d choose d, so dimension of f to the E is cardinality of E, so which is less than dimension of Vd, right? So you have a linear transformation that maps the space of polynomials of degree at most d to this f to the E vector space, but the origin, the domain has higher dimension, right? So therefore the kernel of T is not non-trivial, right? So dimension of kernel is positive, right? So that therefore there is f which is non-zero such that Tf is 0. And that's it. So that's the proof for the second lemma. Now we are ready to prove. We are ready to prove the theorem, right? Let K be a Kakeya set. Then by two lemmas, it has to be at least n, right? Size of that has to be at least what? N plus Q. Yeah, I didn't say. Yeah, Q plus. What was the? Yeah, what is the degree? Okay, let me say it this way. If the size of K is less than f plus n minus 1, choose n, right? Then there is a non-zero polynomial f with n variables such that f of x is 0 for all x in K, and the degree of f is at most f minus 1, right? But that's contradicting the first lemma. So size of K is at least f plus n minus 1, choose n. And it's easy to see that what is it? F plus n minus 1, f plus n minus 2, f. All right, so you subtract n times, so f divided by n factorial, right? So this is obviously at least f to the n divided by n factorial, right? So that's the proof. It's a very simple proof. On the one side, we prove that there's no polynomial of no non-zero polynomial, which is 0 completely on the Kakeya set. On the other side, any small size set, you can find the polynomial which is 0 on that set. Okay, so that. All right, that's it.